for everybody. It's time to begin the next session, and I will replace Mikhail Kiskin as a chairperson for this session. And the first talk will be the talk of our sponsor of Bruker company. I would like to say that, of course, most of you know, but maybe not everybody, that Bruker is world leader in production of EPR equipment and NMR equipment and many other analytical instruments. And yeah, especially for us, the collaboration with Bruker is always very important. I would like to lift this cap for Bruker and drink a little bit, especially because last week we've just had the installation of our new Alexis finished by Bruker engineer Denis Kuznetsov. And I would like to hand microphone to Thilo Hetzke. Please, the screen is yours. We would like to learn on new developments from Bruker.
Yeah, thank you very much. So I hope everyone can hear me well. Okay, are you seeing my screen? Yeah, okay.
Yes, everything is well.
And okay, now you should also see the presentation, correct? Yeah.
Yes.
Okay, perfect. Then I start. Yeah, thanks for the introduction. So I'm an application scientist at Bruker Biospin. And in the next 20 minutes, I will show you the newest addition to the EPR portfolio. Here you can see the agenda of my talk. So in the first part, I will speak about the rapid scan accessory. So its hardware and what improvement rapid scan brings, for example, in comparison to CW EPR. And then in the second talk, I will talk about the Magnetec ESR 5000, Bruker's latest addition to the portfolio of benchtop spectrometers. Okay, so let's start with rapid scan. For this, you can see on this slide how the sensitivity in EPR developed over the past 50 years. You can see considerable jumps in sensitivity, for example, with the introduction of beta-klystrons or the introduction of the SHQE cavity. What you can also see, however, is that since approximately 1997, the sensitivity has stagnated on a rather high level. And I will show you in the next 10 minutes that rapid scan will be the next big jump in sensitivity in EPR. Okay, so what is rapid scan? Here you can see a schematic description of rapid scan and a comparison to CW EPR. So in CW EPR, the modulation width is typically small in comparison to the EPR line width. And what you do is that every magnetic field point is modulated with a frequency of approximately or typically 100 kilohertz. So this is the lock-in detection. And as a consequence, you observe your signal in a derivative line shape. Now in rapid scan EPR, the modulation width is typically large in comparison to your EPR signal. And the scan rate of this modulation width is very fast in comparison to the relaxation of your observed EPR signal. In rapid scan, you use direct quadrature detection. This means that your signals are observed in an absorptive line shape. And due to the rapid scan rate, the EPR spectrum is acquired multiple times for rapid signal averaging. And because of this technique, rapid scan has some advantages over continuous wave EPR, which I will, as I already said, outline on the next slides. So how does typical data processing in rapid scan look like? So normally you always acquire your or typically you acquire your time domain data. So you have an up sweep and you have a down sweep. And because of the quadrature detection, you have your real part and your imaginary part. and then the time domain data is converted into field domain data. And this can be done either by a normal mathematical transformation or a Fourier deconvolution. Oops. How does the rapid accessory look like? So here you can see a picture of the RapidScan accessory. It is compatible with 10-inch magnets and worked with EMX Plus or Elexis bridges. And everything starts in the RapidScan driver unit, where the waveform is generated and then sent to the RapidScan coils, which are attached to the magnet. Now, depending on the waveform you choose, it may be necessary to use this capacitor block here, but more on that later. The microwaves comes from the bridges here, goes through the front end, and from the front end in the resonator, where it interacts with your sample. Then the signal goes back to the front end, and from the front end to the acquisition unit, where the time domain data is digitized and then sent to the computer. I should mention that operation of the whole RapidScan accessory is fully implemented into XEPR. And here is the, so this is our external cooling unit, and this external cooling unit is used to cool the RapidScan coils here. Okay, so let's have a more detailed look at some of the hardware components of the RapidScan accessory. Here you can see the RapidScan coils. So you can use a maximum scan rate of 13 megagauss per second. As I already said, you can choose between different waveforms. So we have the sinusoidal on-resonant mode, and we have the triangular non-resonant mode. For these two modes, different scan frequencies are available. And then here you can see the maximum scan width that can be achieved for a certain frequency for these two waveforms. Now, if you are interested in a larger field range than 200 Gauss, you can use the so-called segmentation experiment, which is implemented in XEPR. And here, different triangular scans are combined. And so you can sample also a very large magnetic field range, for example, to study transition metals. Then here you have the resonator. Here you can see it is installed to an helium cryostat. So this already tells you that the RapidScan resonator is fully compatible with helium and liquid nitrogen variable temperature units. The resonator itself can be critically coupled for a wide range of Q values, so from 500 to 6,000. And critical coupling is possible up to values of 500 milliwatt. Now, how can critical coupling at different Q values be achieved? This is possible because every RapidScan resonator has turns of microcapillaries that are built around the cavity. And these capillaries can be filled with water by a hand-operated syringe. And then here on this graph, you see the Q factor and also the spectrometer frequency as a function of the number of filled turns with water. You may ask, why is this needed? So actually, there are some very specific samples where lowering the Q values is needed in order to obtain the best spectral resolution. And this is shown here on the next slide, where we have PNT, so an organic radical with many narrow lines. But before we look at the spectra, let's look at this relation here. So this is a very general and important concept for RapidScan. So the resonator bandwidth should always be larger than the signal bandwidth. And the resonator bandwidth is inversely proportional to the Q value, and the signal bandwidth is inversely proportional to the line width and proportional to the scan rate. This means that if you have a sample with a very narrow line width, you should either use a small scan rate or a small Q value to maintain this relation and make sure that your spectrum is not distorted. Now here you can see the RapidScan spectrum of PNT for two different Q values. And you immediately see that for high Q values, your lines are broadened and have a rather asymmetric line shape. And this is because this condition here is not perfectly fulfilled. Okay, so let's speak about the advantages of rapid scan. One big advantage is that rapid scan is far less prone to microwave saturation than CW EPR. And this is shown in this graph here, where the signal intensity is plotted as a function of the square root of the microwave power. And of course, one wants to operate under non-saturation conditions, so in this linear regime. And you immediately see that this linear regime for rapid scan is much larger than for CW EPR, which ultimately means you have a higher signal amplitude and higher signal to noise ratio in the same time window. Now, of course, a microwave power behavior cannot be generalized because every sample has the power dependency depends on your sample. But a very nice sample to demonstrate the power or the microwave power advantage of rapid scan are diamonds. Now, EPR can be used to investigate the purity of diamonds, but unfortunately, CW EPR is not so well suited since diamonds saturate at very low microwave powers already. So here you can see in green EPR spectrum of diamond recorded in approximately 2 minutes with an attenuation of 60 dB. And you can clearly see that's a very noisy spectrum, no signal at all visible. But if you then use rapid scan, you can use attenuation of up to 30 dB. And in the same time frame, you get a much better signal to noise ratio. Another sample is irradiated alanine. So irradiated alanine is a reference standard in EPR dosimetry. And of course, if the irradiation dose is high, also your alanine signal is rather strong. But if your irradiation dose is rather small, also your signal becomes small. And here then also rapid scan becomes advantageous because also for alanine, rapid scan has much better saturation behaviors than CW EPR. So here you again see the saturation curves, and here you see the CW spectra and rapid scan spectra. So the rapid scan spectra is after a pseudomodulation to make it comparable. And you can see that rapid scan has an signal to noise factor improvement of approximately 15 while keeping the same line shape as the CW EPR spectrum. I should maybe mention that here these power saturation curves for rapid scan, they can be easily recorded within XEPR because also for rapid scan EPR, XEPR supports all the 2D experiments that you might know from normal CW EPR. So for example, field versus microwave power. Okay, so then another clear advantage of rapid scan EPR is its unprecedented time resolution, which allows to observe kinetics in a time-resolved manner. So this means you are able to observe the kinetics of or observe spin trapping of reactive oxygen species or also light excitation experiments. And what we did in this experiment here is that we took an BDPA crystal and let it fall through the rapid scan resonator while constantly acquiring a rapid scan signal. And the experiment we run was a field versus time experiment. And the exciting and also new thing about this experiment is that the time delay between the slices here was 0. So you didn't lose any time in going from this slice to this slice. And the resolution of this experiment is solely determined by the number of accumulations you take on each slice. So in this case, we used 25 accumulations, which means we had a time resolution of 1.25 milliseconds. So if you now look at the integrated signal amplitude as a function of time, we get this graph here, and you can see that it takes approximately 80 milliseconds until the BDPA crystal has fallen completely through the resonator. And if we now use this value and insert it in this equation here, which is the equation of a free falling object, we get a distance of 31.4 millimeter, which is pretty much the active height of our rapid scan resonator. Okay, so now a slightly more application-orientated example for the good time resolution of rapid scan EPR. So on this slide, we used rapid scan EPR to observe the kinetics of tempo reduction by diethionide. And again, we did a field versus time experiment. You can see really that for every time point, we get the full spectrum. And if we now sit at these two magnetic field points and monitor the signal amplitude at the function of time, we get these two nicely resolved time kinetics. Okay, so with this, I'm at the end of the first part of my talk, and I would now like to talk about the second part of the talk, which is the Bruker Magnetec ESR 5000. So the latest addition to the portfolio of EPR benchtop spectrometers. Here you can see a picture of the ESR 5000. It has a rather compact design, so it only weighs 45 kilograms, which means it is very mobile and can be easily transported by 2 persons. It runs on a Windows platform, and its software called ESR Studio. So here you can see an example of ESR Studio. Supports filtering, baseline corrections, the calculation of your signal to noise, of your double integral, and many more things. It operates at X-band frequencies, has a concentration sensitivity limit, which is smaller than 30 micromolar, a sweep range of 6,000 Gauss with approximately 250,000 points. Another really nice feature of the ESR 5000 is that it supports many accessories. So these accessories range from an automated goniometer over an automated sample loader, various flow and flat cells, various temperature control units, and also various optical accessories. Now, of course, I won't have the time to go through all of these accessories, but please, whenever you have questions regarding the accessories or the ESR 5000 in general, feel free to contact us. Now, I want to talk a bit about the or about some of the variable temperature unit accessories. And here on the left side, you see the temperature control unit. And as you can see, it uses liquid nitrogen and an evaporator that is inserted in the dewar to achieve temperatures in the range of 93 to 473 Kelvin. And the nice thing about this accessory is that it is fully implemented into ESR Studio. Then, of course, we also offer a liquid nitrogen dewar, so a finger dewar. And this accessory allows for quick and easy low temperature measurements at 77 Kelvin. And here you can, for example, see an EPR spectrum of the nitric oxide hemoglobin complex recorded at 77 Kelvin with the ESR 5000 and the finger dewar. The other accessories I want to present you are the optical accessories. And here on the left side, you can see the optical stimulation units. So these are rather compact accessories that operate at a single wavelength. So for example, with an output power of 400 milliwatt, it's 365 nanometers, and other wavelengths up to 800 nanometers are here available on request. Then we also have the Hamamatsu optical stimulation units, which are mercury xenon lamps. And of course, these accessories have a broader spectral distribution. And also here, we offer different spectral distributions. Now, the nice thing about the optical accessories, and this is true for most of the accessories, is that also these accessories are fully controlled by ESR Studio. So this means you cannot only turn the lamp on or off, you can also change the intensity from 0 to 100%. You can define a lead time, you can define a sleep time, and so on. Okay, so the last accessory I want to present to you is the spin count accessory, which allows for a reference-free and absolute quantification method. And you can start spin count by clicking this button here in the measurement list. And then this window here will appear where the user is asked for some sample information. So you have to give the height of your sample, the diameter, and if you want, you can also give the mass. And of course, you have to give your electron spin. Now in the measurement view, these qualifiers, or these two qualifiers here appear. Now the green qualifier is used for fitting of the baseline. Then the baseline is subtracted from the whole spectrum. But of course, the double integral is only computed for this blue region here. If you want to change the borders between these qualifiers, this can be easily done with the mouse. So if the user is finished with giving all the user input, the user can click on the calculate button, and then the spin count report is given, which contains the absolute number of spins, the spin concentration, the time point at which the spectrum was acquired, start and end of the qualifiers, and so on. And as you can see, this also works nicely for 2D data set. So here you can see a Fenton DMPO assay. So this spin count report can now be exported and plotted with an external program. Another possibility is to use the inbuilt evaluation function of ESR Studio. And here, for example, the double is plotted as a function of the time. And you can see here nicely the exponential decay. So with this, I'm at the end of my talk. I would like to thank you for your attention, and I'm happy to answer questions. Thanks.
Thank you very much, Thilo. Do we have any questions? We have some time for questions. May I ask the first one?
Sure.
So rapid scan, if I understand correctly, I mean, one of its advantages is that for saturating samples, it kind of turns the weakness into the strength. If we deal with magnetically concentrated samples, where basically you cannot normally saturate, do you still expect some advantage in sensitivity, or in this case, it will be comparable for rapid scan and for normal CW-EPR? For fast relaxing, non-saturating systems like coordination compounds normally, yeah.
So I think this is always a bit, of course, it's always a bit sample dependent, but I assume or I know that you also gain here in sensitivity. Yes. Yes.
Can you?
So because also these samples will saturate at higher microwave powers. So therefore, also for these samples, you can use higher microwave powers than for CW-EPR, which means you get a higher signal amplitude and therefore a better signal to noise.
No, maybe I mean other way around, that the whole power that you can supply is not able to saturate the sample. For example, this case.
Okay.
Then you probably have advantage of 1 over frequency noise. But can you give us some feeling for such samples, how much the anticipated gain could still be? Difficult to say, yeah.
Yeah, it's difficult to say. I mean, of course, for rapid scan, you don't want to operate in the saturation regime for rapid scan, right?
Right.
Yeah. But giving it's always difficult to give a value for. It's always difficult to give a general value. So. Yeah.
Yes, thank you anyway.
Yeah.
Maybe we have other questions. Just in case, if you have your questions later, you can probably directly contact Bruker.
Sure.
Yeah. And thank you once again, Thilo, and thanks to Bruker for sponsoring us.
Thanks. You're welcome.
Yeah, thank you very much. So then we switch to the next talk, and the next talk will be given by Professor Alyona Starikova. It's my pleasure to introduce her. She works in Southern Federal University, and the title of her talk is Computational Modeling of Cobalt and Iron Complexes with Dioxolenes Bearing Stable Radical. Alyona, please go ahead.
Thanks for the introduction. Hello, everyone. Let me thank the organizing committee for the opportunity to present my report, which is devoted to the computational study of metal dioxolene complexes bearing stable radicals. The development of open-shell transition metal complexes exhibiting variability of the magnetic properties represents a promising direction of chemistry and material science. Such magnetically active compounds can find applications for the design of molecular switches, magnets, memory devices, and spin qubits. And the most versatile mechanism of switching the magnetic characteristics under the action of the external stimuli include spin crossover caused by the electronic rearrangement within the valence shell of a metal ion, and valence tautomerism or redox isomerism, a reversible intermolecular electron transfer involving the metal center and the coordinated redox active, most often dioxolene ligand. A widespread type of coordination compounds exhibiting magnetic stability are the salt-like complexes comprising one dioxolene ligand and tetradentate nitrogen donor base. The uniqueness of such molecules consists in strong dependence of the mechanism chosen by a molecule for the occurrence of a spin transition, spin crossover, or valence tautomerism on the nature of the metal ion and the structure of the ancillary ligand. Of special interest are the molecules containing an additional radical group that ensures the paramagnetism of all the electroners. According to the Mossbauer spectroscopy and magnetic chemical data, an iron-3 complex with a tris-2 pyridylmethylamine base and the catecholate ligand bearing nitronil nitroxide substituent exhibits spin crossover transition. So the aim of the present study was to search for new heterospin systems that are prone of changing their spin states via spin crossover or valence tautomeric rearrangements. And with this in mind, we performed a DFT computational modeling of the electronic structure, energy characteristics, and magnetic properties of the mononuclear salt-like complexes of cobalt and iron with the tetradentate nitrogen donor bases, pyridinophanes and tris-2 pyridylmethylamines, and dioxolene ligands comprising organic radicals. At first, we have considered structural analogs of experimentally investigated iron-3 catecholate nitroxide spin crossover complex. The results of DFT calculations of the latter predict the destabilization of the high spin isomer by 10.3 kilocalories per mole relative to the low spin one. It can be assumed that the iron compounds investigated with the use of a chosen approximation will prone to spin transitions and the calculated energy difference of about 11 kilocalories per mole. According to the computational results, the low-spin electromers 1, 3, and 5 correspond to the ground states of the complexes with the unsubstituted tris-2-pyridyl-methylamine ligand. The unpaired electrons in these structures are concentrated on the radicals and the complexing ion, and the part of spin density of the metal center is located at the oxygen atoms. These findings are in agreement with the X-ray and Nussbauer spectroscopy data for similar iron-3 complexes, indicating an admixture of the electronic configuration comprising ferrous ion and semiquinone. The geometry optimization of the complexes on the accepted potential energy surface led to the isomers 2, 4, and 6, bearing also two paramagnetic centers, the high-spin trivalent iron ion and radical substituent. Closeness of the calculated geometry parameters of the coordination sites of the electromers with various radicals is reflected in the same values of the energy differences, 11.4 kilocalories per mole, witnessing the possibility of spin crossover transitions. A computational study of exchange interactions indicates strong ferromagnetic coupling of paramagnetic centers in the low-spin electromers and moderate ferromagnetic exchange in the high-spin structures. Therefore, the considered complexes will possess ferromagnetism. And the predicted character of exchange interactions is in agreement with the shapes of magnetic orbitals exhibiting an absence of the antiferromagnetic exchange channel. The calculations of the compounds with the two metal substituted tris-pyridyl-methylamine have shown the elongation of the iron-nitrogen bond lengths. And the resulting non-equivalence of the coordination bond distances, which is more pronounced in the low-spin electromers, lowering the stability. And as a consequence, the energy difference between the low-spin and the high-spin states decreases sharply in comparison with the values found for the derivatives with the unsubstituted TPA ligand. The predicted values, not exceeding 5 kilocalories per mole, allow one to expect the probability of spin transitions. The presence of a third metal substituent in the tetradentate nitrogen-containing ligand results in additional distortion of the geometry of the coordination site in the low-spin structures and inversion of the relative energies of the electromers. The ground states of the complexes are presented by the high-spin isomers, characterized by ferromagnetic exchange interactions of moderate strength. Inclusion of a phenylene linker into the dioxolene moiety does not exert a significant effect on the coordination bond length. The energy differences between the electromers of the complex with the unsubstituted TPA and that in which ancillary ligand comprises two methyl groups make it possible to expect realization of spin transitions. Three alkyl substituents create steric hindrances for the formation of a short coordination bonds in the low-spin isomer, which entails its destabilization. This compound will be in the high-spin state. The presence of a phenylene linker leads to a decrease in the values of the exchange spin coupling parameters, conditioned by the elongation of the distances between the paramagnetic centers. The low-spin isomers are characterized by ferromagnetic exchange of moderate strength, while in the high-spin species, unpaired electrons virtually do not interact. The calculations of radical substituted dioxolene complexes of iron with the pyridinophane derivatives have shown that the variation of the alkyl groups at nitrogen atoms of tetraether microcyclic base and the radical substituents in the dioxolene moiety does not lead to change in the electronic structure. The electromers contain dianionic catecholate form of the dioxolene and three charged iron ions. As the volume of the alkyl substituent in the tetraether microcycle increases from methyl to tert-butyl, the energy difference between the isomers reduces from 12.5 to 3.7 kilocalories per mole in favor of the low-spin electromers. The predicted data allow one to expect realization of spin crossover. It should be noted that crystal package effects, which are not taken into account when performing DFT calculations of a single molecules, can lead to the fact that the complexes with isopropyl and tert-butyl derivatives will be in the high spin state in a wide temperature range. Similar situation was observed earlier when studying the iron complex with the 3,5-diterbutylone-2-dioxolane. The spin density of a tempo radical is located at the nitrogen and oxygen atoms and is separated from the pi system of the quinone ring by the aliphatic bridges. As a consequence, the exchange interactions between the tempo substituent and iron center are absent. In the compounds with the dioxolane comprising third butyl hydroxyl, the presence in the magnetic orbital of the contributions of the iron atom, quinone ring, and the radical provides for the formation of exchange channel and the appearance of strong antiferromagnetic exchange interactions. Inclusion of a phenylene linker lowers these values, but still antiferromagnetic exchange can lead to the diamagnetism of the low-spin isomers. In the complexes with the nitronyl nitroxide, the orbitals of iron ion and the radical do not overlap, which results in ferromagnetic coupling. Thus, variation of the type of the radical allows one to control the exchange interactions in the studied iron systems, which are potentially capable of undergoing spin crossover transitions. Let's turn to the consideration of cobalt compounds. As follows from the experimental investigation of cobalt complexes with the 3,5-diterbutylone-2-dioxolane and 2-spuryl-methylamine bases, the systems with unsubstituted and 1-methyl substituted TPA can be described as a diamagnetic cobalt-3 catecholated derivatives. 3 methyl groups in the 6th position of the pyridine moiety stabilizes the high spin quintet state, while 2-methyl substituent compound undergoes valence to automeric interconversion at room temperature. And taking into account for the computational results of the 2 experimental complexes, it can be assumed that analogous cobalt compounds studied with the use of a chosen approximation will prompt to valence to automeric transitions at the calculated energy difference of about or less than 5 kilocalories per mole in favor of the low spin isomer. Typical spin density distribution of the found electromers is presented on the top of the slide. As follows from the data collected in the table, the presence of a radical group does not exert significant effect on the capability of the cobalt complexes to the redox transitions. As in the experimentally studied series, only compounds with a 2-methyl substituted TPA can possess valence to automerism. Depending on the way of attaching the radical directly or via phenylene linker, the alteration of relative energies is in the range of about 1 kilocalories per mole. According to the computational results, regardless of the number of methyl groups in the TPA ligand, the type of the radical substituent and the way of its attachment, the exchange interactions between the cobalt ion and semiquinone J1 bear a strong ferromagnetic nature. This finding is in agreement with the data for analogous complexes not containing radical substituent. In the complexes bearing radical substituent directly connected with the dioxolane moiety, a strong ferromagnetic exchange coupling of 2 organic moieties is expected. The metal ion and the radical group J2 virtually do not interact. Insertion of a phenylene linker does not alter the nature of the magnetic exchange, but expectedly leads to a sharp lowering the exchange coupling of 2 organic radicals. And finally, the last series of compounds. As it was presented in Professor Kulet-Boskvich's report, a comprehensive investigation of a cobalt complexes with the 3,5-diterbutylone-2-dioxolane and the pyridinophane derivatives was early performed. And let me remind you that increasing the size of the alkyl substituent in the tetraaza microcycle promotes lowering the energies of the isomers comprising divalent ion and semiquinone relative to the low spin diamagnetic electromers, which results in favorable conditions for realization of a valence to automeric interconversion in the complex with the isopropyl derivative. Upon further increase in the bulkiness of the substituent, there is an inversion of the relative energies of the isomers comprising the low spin metal ion, thus establishing the conditions for spin crossover rather than the valence to automeric transition. Therefore, variation of alkyl groups in the pyridinophane allows one to control relative stability of the electromers and as a consequence, the type of the mechanism of spin state switching. As follows from the calculated energy characteristics, regardless of the presence and the type of the radical, complexes with methyl and ethyl substituted pyridinophanes will exist in the low spin doublet state. Moving to the complexes with the isopropyl derivative is accompanied by reducing the energy difference between the low spin and the high spin isomers to the values indicating the possibility of a balanced tautomeric rearrangement. In the compounds with the third butyl substituted pyridinophane, spin crossover transitions are expected. The computational results obtained are in agreement with the data found for the Cobalt compounds not comprising radical groups, which witnesses insignificant effect of the radical on the energy characteristics. The calculations have shown that the exchange interactions between the metal ion and the semiquinone bear strong ferromagnetic nature in the low spin isomers of the third butyl substituted derivatives and moderate antiferromagnetic exchange in the high spin electromers. Regardless of the spin state of the divalent cobalt ion, the metal center and the nitronil nitroxide radical are antiferromagnetically coupled with the moderate strength. At the same time, the exchange between the semiquinone and nitronil nitroxyl have strong ferromagnetic nature. Temper radical, as in the considered earlier compounds, virtually do not interact with the other ferromagnetic centers. To sum up, among the investigated iron and cobalt complexes, the systems potentially capable of spin state switching rearrangements via spin crossover or balanced tautomeric mechanisms have been revealed. Rational choice of a radical substituent allowed us to control the character of exchange interactions in which it involves, while relative energies of the electromers depend on the structural peculiarities of the ancillary nitrogen donor base. And the advantage of the studied cobalt complexes over their analogs not comprising radical groups is the paramagnetism of all the electromers. In the development of this direction, we are going to consider species with the dioxolenes bearing phenylalanine derivatives. A distinctive feature of this polycyclic hydrocarbons consists in increasing the number of unpaired electrons with increasing the number of six-membered cycles, which can expand the potential applications of the proposed coordination compounds. Thank you for your kind attention.
Thank you very much for the very interesting talk. I see already two hands. So the first was Marat Husniyarov. Please ask a question.
Okay. Very nice talk, Alyona.
Thank you.
Great. We saw a lot of numbers coming from DFT and broken symmetry DFT. And if I see a series of compounds and we see that one number is getting smaller and smaller, and I'm perfectly okay with the trend. However, the numbers themselves, so both energy difference between different electronic states and also the exchange coupling constants, they are highly dependent on the functional. So for all your calculations, you are using the same TP-SSH functional that might be probably currently one of the best, one of the most accurate. However, so I still do not believe in these absolute numbers and these absolute values. So are you making any benchmarking? So are you using a series of functional to confirm that the numbers that you are getting, the absolute numbers that you are getting from the calculations, we can trust them?
Mm-hmm. Thank you very much for your attention, for your question. We use the same approximation, and if you notice, the same contour ion in order to be able to compare this results with each other, and maybe in the future to form a database for the subsequent application in machine learning algorithm. But we are ready to use a lot of other approximations when this complexes will be synthesized. So, and maybe to perform some additional calculations in solution or with inclusion of dispersion interactions.
Okay, so
because we can, as there are no in the experiment, we cannot compare, we cannot match the results. So the results of calculations with the potential experimental results.
okay, I got this, but you can apply your protocol to known compounds to verify how accurate actually your calculations are. So have you done this?
Well, as I shown before, we calculate the experimentally well-known compounds.
Okay, okay.
For example, for the Cobalt complexes, sorry. Okay, here, for example, this completely experimental study, and now we can say that, for example, about 5 kilocalories per mole is okay for VT, but higher than, for example, 6 kilocalories per mole, it's it is too high energy difference, etc.
Okay, okay. So you are aware of the range that you can trust at the end. Right? So you are aware of your accuracy.
Yes, but plus minus 1 kilocalories per mole, which is the error of DFT calculations, 1 or maybe 2 kilocalories per mole.
Okay.
Thank you.
Thank you.
Mikhail Bubnov, please. Microphone is yours.
Alyona, thank you for your bright presentation. I have a short question concerning this slide. To my opinion, in the case of ethyl substituent, there should be the electron transfer corresponding to conversion of Cobalt 3 into Cobalt 2. Why it is not observed?
Thank you for the question. Yes, according to the calculations, this transfer is probable, but in the experiment, this compound is purely in the diamagnetic state over the wide temperature range and in the solution and the solid state. So I think that the calculated energy accessibility does not mean absolutely the experimental reaching this state. So it can be, it is possible, but in the experiment, we do not see this isomer.
So I have one short additional question. Are you sure that you have observed low spin Cobalt 2? It is
no, we observe a low spin Cobalt 3 halate, the diamagnetic state.
In the case of treasury butyl.
Terbutyl? In the case of
Cobalt 2.
In the case of terbutyl, yes, we observe the spin crossover, low spin divalent. And not only we, but in the 2010, the work by Kruger et al., as it was demonstrated in the Professor Khaled Boskovich report. It is the first example of a Cobalt dioxolene complex which exhibits spin crossover rather than valence to rearrangement.
I understood this. Thank you.
Thank you.
We have 1 more minute. May I ask a short question? This upper plot here, one with nitronil nitroxide, another with tempo radical, and you have calculated also the influence of these exchange couplings somewhere later. So I have very simple questions. Basically, these 2 radicals look like 2 limiting cases. For nitronil nitroxide, you have really electron density close to the linker, and for tempo, it's other way around. Do you have idea of something in between to check your conclusions?
And we also performed the calculations with the diethiodiazolate and terbutyl nitroxide, but terbutyl nitroxide is strongly antiferromagnetically coupled with the other radicals, so it is well, not desirable. And also the verdazole, but the verdazole is the results of the calculations with the verdazole radicals are very close to the nitrogen nitroxide radical.
Yeah, well, clear. It's also electron density delocalized. Yeah, thank you very much. It was a very interesting talk, and we are just on time. And we move to the next talk, and it's my great pleasure to introduce next speaker, academician Professor Viktor Ovcharenko from our Institute, International Tomography Center. And the title of his talk is Novel Organic Magnet. Viktor Ivanovich, please, the screen is yours.
Thank you, Matei. Let me open my screen. Yes. Is it okay?
At the moment, we do not see the screen.
You cannot see my screen? My screen?
No, not yet.
No, not yet. Excuse me. Excuse me. Excuse me. My screen. Okay. Alyona. Yes. Очень хорошо. Yes, okay. Yes. Закрывается.
Отдельно PowerPoint открывайте прямо.
Окей.
Ага.
Отменно. Нет.
Закрылось.
Так. Закрыть другому. Демонстрация экрана.
Демонстрация идет. Уже идет вот эта презентация.
Матвей, what about my screen? Do you see my screen?
No.
No. Okay, wait a little bit. Wait, one moment. One moment, wait. PowerPoint. Файл. Опубликовать. Так.
Просто открывается. Просто пусть она висит, открыто, все. Все, отлично. Теперь заходите в обратный зум.
Окей.
Поделиться.
Поделиться.
Кликайте сначала на экран. Ага, поделиться. Это давайте презентацию. Все честно, демонстрирую. Все. Слайд-шоу, пока слайды.
Так. Окей, окей.
Все, все.
Is it okay?
No, no, no screen.
My God, what happened? No screen. Окей. What happened?
Давайте еще раз зум.
Еще раз зум. Есть, это зум.
Догоди. Сюда.
Сюда.
Поделиться.
Поделиться.
Все. Приложение. Все.
Написано, можете демонстрацию.
Подожди. Да, все правильно. Нет, нет, все правильно.
Пауз демонстрации.
Вы открываете, да? Видно?
Да, сейчас видно, нужно сделать только на полный экран, нажать там на...
F5 или пока слайд.
Да, окей, окей. Is it okay?
Perfect.
Oh, thank you so much. Excuse me, something was wrong. Hello, everybody. I would like to present our data recently received. In detail, it's better to say that I would like to discuss highly stable radical derived from peers-induced fluorescence and perfect experimental support of McConnell-1 exchange model. This investigation has been made in collaboration of two teams from Institute of Organic Chemistry in Moscow and International Tomography Center. First of all, let me introduce my colleagues. Mikhail Yegorov, Mikhail Saraevsky, Anna Kuznenkova. It's a team who performed electrochemical measurements. Vitaly Morozov, who performed quantum chemical calculations, Sergei Fokin, both of them were involved in synthetic investigations. Artem Bogomyakov performed magnetochemical measurements, and Galina Romanenko was responsible for X-ray investigation of simple crystals. And you know that stable organic radicals are of great academic interest. At the same time, they found a lot of different practical applications and applications in our science. And the good idea is to create new types of different magnetic electric compounds that saturated with organic components based on our very common synthetic chemistry approaches. You know, this would impart the properties typical of organic compounds, such like low density, elasticity, transparency over a broad range of electrochemical spectrum, high resistance to electric current, biocompatibility, and now we speak more and more about recyclability. This is really important, and we pay attention for this moment. Persistent organic radicals are considered also to be promising building blocks for multifunctional molecular-based magnets and molecular materials, and this is important for design of different devices. However, it's really very rare even to synthesize reliably and reproducibly recorded bulk magnetic ordering for organic compounds. This is an extremely rare event. The structure of some such compounds is given in this picture. You can see lithium salts of tetracyanate ethylene that has been discussed in the first journalist presentations yesterday. There are a lot of problems with pure organic magnets. Sometimes they possess extremely low magnetization. Extremely low. This is typical for not on the described organic polymers that show bulk magnetization at room temperature. Very often, these compounds are sensitive to oxygen or air moisture. Moisture is really a high problem for many pure organic magnets. And we need to find new compounds possessing new set of physical chemical properties which may be useful to study in the field of molecular organic magnets. But how to find these compounds? Usually we found this compound by chance. The same case happened with us, and today I would like to present a new type of highly stable radical derived from pyrazine-fused fluorescence. This is well-known compound, and you can see a few papers. It's not all. In fact, it's maybe 3-4 times more. But this compound previously investigated only in the chemistry of so-called energetic materials. Fluorescence cycle possesses high energetic capacity, so special chemistry of energetic materials use such derivatives. But I have to stress, usually in the articles we write that be careful. You have to be safe if you manipulate in the right way with such compounds. You have to take into account differently diffusions like cloud, steam, and so on. But at the same time, in any publication, you find information, and the same you can hear from me. When we investigated this compound, it was absolutely stable, even under heating, in water solutions, in organic media. Or if you keep solid sample, this compound was absolutely stable. And I would like to stress a few moments that you find during the investigation of this compound. Difluorosanopyrazine radical anion is really highly persistent compound, highly persistent under ambient conditions, even in aqueous solutions. It's very important. We crystallize salts directly from aqueous solutions. All solids have the same structure. They contain columns of radical anions. Quantum chemical study of salts revealed unusual effect. The exchange coupling energy between the neighboring radical anion provide highly sensitive to the location of one radical anion related to another. And we were surprised. We didn't suggest at the beginning that we found this result. The data obtained turned out to be perfect experimental support of McConnell exchange model. In this picture, you see starting difluorosanopyrazine and two its deprotonated derivatives, and also the product of the oxidation, this protonated radical. But protonated radical is kinetically not stable. All radicals are not stable in acidic medium. And here is very stable radical anion. And below you can see this sample as needle. Needles are very tiny because this compound deeply colored, and it's necessary to prepare very tiny symbols so that it's possible to see actually with this deep green coloring. It's possible to synthesize this so-called radical. This radical was described earlier, and nobody investigated magnetic chemistry of such compound, but it was suggested that this is really radical. In fact, this compound is absolutely diamagnetic. Absolutely. It's not possible to reduce the ESF spectra. It's possible to say that it is radical, but it's very special radical, so-called singlet radical. It means that singlet state is very low and excited by radical state is very high. It means that is again the conditions absolutely diamagnetic compound, and where electrons only is addition to chemical bond. We investigated in detail in different media and the different conditions, the different pH, their electrochemical properties. As you see in the picture that is shown in alkali media, their oxidative potential is less and less. So in alkali media, it's easy to synthesize this anion radical, and this anion radical is stable. It's possible to find the range of oxidation potential where it was possible to recycle, to realize cyclic redox process. And you see at the same time the color of study compound. This is color restoration, radical alignment colored in green, and so-called singleton radical is deep red, but slow coloring is due to low solubility in water. You see experimental and theoretical ESR spectra showing that we really manipulate this compound. We use in our experiments two oxidants. Earlier, our colleague used very strong oxidants like anhydrous nitric acid, fluorine, or chlorine. But we used bromine, gaseous bromine, or lead dioxide. We used such oxidants because it was easy to stop oxidation process. For example, if you take off lead dioxide and stop further oxidation. Let me show film. I don't know if you will see, if you will be lucky. We prepare a special flask, introduce its water solution, introduce its solution, starting diphorozamic erosine, and then there is no stopper. We introduce tube, and through this tube arise bromine vapors. Maybe you see that its surface appears green coloring. It's big, so it's possible to visualize reaction and to show any radical formation. It goes in solution slowly, without stirring. It's a slow process. And then please pay attention on the surface of the solution. Then slowly appears brown spots, brown coloring. It means that at the surface appears more and more singlet biradical. Of course, and if you mix the mixture, there are a lot of starting compound, and there will be co-proportionation between single radical. Okay, let me go further. Oh my God. You see only one slide. I tried. Okay. Okay, it's okay. We group crystals for all compounds from water solution, and we found that all crystals consist of column of anion radical. This is example for ammonium salt, but the same columns you see for lithium compound, for potassium compound, and for sodium compound. What is important? Typical temperature dependence for magnetic movement is like this, like for lithium compound, like green one. Green line is theoretical, and something special we found for sodium salt. This temperature decreasing, effective magnetic moment is growing up. I skip this explanation of anti-magnetic interaction in the salt to understand why only sodium salt possess ferromagnetic exchange interaction in solids, and this compound is able to magnetize at lower temperature, at temperature lower than 0 Kelvin. We legislated stable magnetization of this compound. This is real organic magnet, new type of organic magnet. What is the reason for magnetization for this compound? So I finished my initial time. We made a lot of quantum chemical calculations and constructed special energetical diagram. If you move one radical along another and on the side direction, we found that there are alternative areas of exchange direction. Ferromagnetic one marked for yellow, and green and blue are anti-ferromagnetic one. Let me put on this on my screen experimental data for ammonium salts, lithium, and other salts, and you see only sodium is in ferromagnetic area. After the analysis of strain density for this compound, we found that this compound is very good example to demonstrate Marconi rules. If there is overlap of strain density of different sign, like in sodium compound, we have ferromagnetic exchange direction. And if overlap electron densities with the same sign, like in potassium, lithium compound, or others, we have anti-ferromagnetic exchange direction. So, at the end of my presentation, I would like to stress that we found you represent new chemical class where it's possible to find pure organic molecular magnets. Thank you for your kind attention.
Thank you very much. This lecture is open for discussion. Are there any questions? Sergey Weber, please.
Mr. Ivanovich, so you showed us compounds which have a similar chemical structure, but very different color of compounds. Sorry if I skip it, but can you comment on the influence of probably structural features of crystal packing to the color of these compounds?
No. There is no connection between crystal packing. I have shown solutions, and you can realize oxidation in solution when appears radical anion, immediately appears deep green coloring. It's the same experiment. It's possible to realize during oxidation in electrochemical cell in ESR spectrometer that was made in the Institute of Organic Chemistry in Moscow by my colleague Lala. It's very good demonstration of coloring appearance in solution when you introduce electrodes and then begin to oxidize the mixture. That contains color starting resin compound.
Thank you.
Another question from Marius Andruch, please.
Yes, Andruch.
Please switch on your microphone.
Very nice and interesting talk. Thank you so much. And I have a question concerning the packing diagrams you have shown for the compounds containing simultaneously ammonium and water molecule. It was possible to make the difference between them? I mean, did you see the hydrogen atoms, or there are some particularly interesting hydrogen bond interactions between these two molecules? I mean, ammonium and water.
Oh, yes, yes, thank you for your question. When we made quantum chemical calculation, we included calculation neighboring molecules, we include water molecules and ammonium, and we found that exchange direction between radical anion that are in different columns are very, very small. It's around 1 to wave numbers, not more. Sometimes even less than one number. And main exchange direction concentrate inside the column. We analyze these different approaches, quantum chemical approaches, and periodical calculations, and result was the same. We were lucky that structure of all salts are very close, but there are slightly different because they move one along another and technical directions, to opposite directions. And when we analyze this, we understand, and the distance is really very short, at around 3.2 angstrom. So it's clear that my direction in that side between two and an radical. It's typical back-quantum exchange, and we are lucky that in parallel planes they are in the same direction. And making many calculations, we exclude interaction between columns.
Okay, thank you.
Thank you.
Yes, thank you very much. And we have to move to the next talk, to the last talk of this session, which will be given by Artem Bogomyakov from International Tomography Center. And he will talk on heterospin pressure sensors. Please, Artem, go ahead. Don't forget to switch on your microphone. It's now switched off. Artem.
Yes.
Yes.
Could you hear me?
Yes, now we can hear you. You need to make it full screen. And okay. Yeah, please.
Yeah. Thank you, Mr. Chairman, for your kind introduction. I would like to present my work about heterospin pressure sensors. So heterospin complexes that undergoes magnetic anomalies with lowering temperature based on hexafluoroacetylate of copper and nitronil nitroxides. So structural transitions in such complexes results in changing of coordination mode of radicals. So when radicals are axially coordinated, usually weak ferromagnetic or anti-ferromagnetic coupling is observed. When radicals became to equatorially coordinated, typically strong anti-ferromagnetic coupling are observed for the system. In results, some spins in the system are vanished. The first example of the complexes in which spin transition and magnetic anomalies was found is such tetranuclear complexes with pyridyl substituted nitronil nitroxide. When lower in temperature, you can see abrupt decrease of Kt value, and magnetic anomalies and structural transitions occurs between 100 and 150 kelvins. Nowadays, there are several kinds of complexes are known. This is tetranuclear complexes, cyclic dimers in which two copper atoms linked by two nitroxides to form cyclic dimers, in which a radical coordinated to one copper atom by nitroxide group and donor atoms of pyridine ring to another copper atoms. The similar complexes with polymer chain structures in which cyclic dimers are linked by additional copper hexafluoroacetate in polymeric chains, and two classes of polymer chain complexes with head-to-tail motif in which radicals coordinated to two radicals coordinated to one copper atoms by nitroxide group and nitrogen atom of pyrrhazole ring, and head-to-tail polymer chains in which there are three spin exchange clusters and isolated copper ions are alternates. To change transition temperature or character of transitions, different modifications of organic ligands were performed. So introduction of ethyl groups in midazoline ring results in smoothing of magnetic transitions. If we change methyl groups in nitrile nitroxide fragment to spiral cyclohexyl groups, pentyl groups, we can see abrupt transitions, and temperature of these transitions can be controlled by changing the substituent in pyridine rings. In case of cyclic dimers, there are different type of radicals. There are a lot of complexes with different type of radicals were obtained. Some of them you could see yesterday in the presentation of Tolstikov Svetoslav with such radicals that will be published soon. And you can see different radicals with which complexes with magnetic anomalies was found. In some cases, in the crystal structure of these cyclic dimers, solvent molecules can be included, and depends on which cavity this solvent goes, the character of magnetic anomalies and temperature of this transition will be different. Of course, changing the substituent in pyridine ring results in different magnetic properties. Polymer chain complexes with cyclic dimer fragments was obtained with such type of radicals, and different substituents result in different magnetic properties and sometimes in different amplitude of transition. In case of polymer chain complexes with head-to-tail or head-to-head motif, head-to-tail complexes was not so big family. One complex was obtained with methyl pyridyl, methyl pyrazole substituted nitronil nitroxide, and another one with ethyl pyrazole substituted nitronil nitroxides with spirocyclic substituents in nitronil nitroxide fragment. In head-to-head complexes, there are a lot of samples with different substituents in pyrazole ring. With two alkyl substituents was very unusual magnetic properties, sometimes in two-step transitions or transitions with huge hysteresis. In case of terbutyl nitroxides, varying of substituent in pyrosol ring results in changing the magnetic anomaly temperature. Of course, a huge family of butyl substituted pyrosols with solvent molecules in the solid structure. The magnetic properties of such head-to-head polymer chains are dependent on which kind of solvent molecules are included in solid phases. Sometimes varying solvents, we can obtain complexes with different, absolutely different magnetic anomalies. So, but which complexes can be used for heterospin pressure sensors? As was mentioned by Professor Malcolm Halcrow, spin crossover is a crystal engineering problem. So what problem should we solve to use these complexes under pressure? First of all, some problem with pyridyl substituted nitroxides is sometimes a gradual transitions or high temperature of the transitions. So at high temperature, the sensitivity of squid magnetometers is low due to Curie law. For the terbutyl nitroxides, there is a low stability of the radicals and so on, of the low stability of the complexes with Z radicals. Some of examples of low stability of these complexes you could see yesterday in the presentation of Irina Golomolzina and Professor Galina Romanenko. And another problem when the solvents are present in the solid phase. When the solvent loses during at high temperature, the magnetic properties may change and magnetic anomalies and structural transitions can disappear. So we stopped on the complexes without pyridyl substituents, without terbutyl nitroxides, and without solvent molecules. First of example is pyrosol substituted nitronil nitroxide with spirocyclopentyl groups. So applying a pressure results in increase in transition temperature that can be clearly viewed on magnetic properties of these complexes. Analysis of magnetic anomaly temperature with applied pressure gives a slope of this curve of about 290 Kelvin per GPa. Of course, these transitions accompanied by changing color and can be viewed by eye without any devices. Another example is similar complexes with head-to-tail motif of polymer chain with methyl substituted pyrosols. Here you can see the same trends on the magnetic properties, and analysis of pressure dependence of magnetic anomaly temperature gives the slope of about 590 Kelvin per GPa. This is one of the record value for the complexes. Applying the pressure to polymer chain complexes with head-to-head motif dramatically changes the temperature dependence of magnetic properties. So at ambient pressure, you can see gradual steps on the magnetic curves, and when they apply pressure, these steps practically disappears, but you can see decreasing of KT value at room temperature. When we plot the KT value at room temperature with pressure, we can obtain the slope of minus 0.34 Kelvin cubic centimeters per mole per GPa. So there are very sensitive to external pressure complexes that can be viewed by magnetic measurements at different pressures. At the end of my talk, I would like to thank my colleagues, Russian Scientific Foundation for the financial support, and thank you for your kind attention. Thank you.
Thank you very much. And the lecture is open for discussion. I see Nikolai Efimov has a question, please.
Yes, thank you, Artem, for your brilliant talk. And I have a questions. Two questions. Below your anomaly, for example, on slide 5, 8, something like that, temperature dependence. That, in one case, you have anomaly and then flat dependence. But in, for example, in this case, in orange dots, squares, you have some rise. What's happened below the anomaly in this case? And
in case of N-propyl complexes, there is transition occurs not in all molecules, but only in part of them. So in part of them, we obtain part of molecules goes to strongly coupled state, and spins of copper and nitroxide are compensated, but another part of molecules in solid structure stay in weakly coupled state with axially coordinated nitroxides. And increasing of KT value or effective magnetic moment value with lowering temperature is caused by ferromagnetic exchange interactions in molecules with axially coordinated nitroxides.
And in this case, I have another question. Is it one phase? Did you check it by X-ray, powder X-ray?
Oh, yes, of course. The structure for such complexes with transitions not in all molecules were solved. So the crystals save their quality with lowering temperature, and the structure for such complexes was solved below the transition temperature.
Okay, it's one phase.
Yes, it's one phase.
Check it.
It's regular phase.
And I have now another question about today. Professor Mondal showed us what he has some difference in magnetic properties due to different external magnetic fields, 100 Ørsted and 1,000 and 10,000. Did you check, did you observe some difference in the case of different external magnetic fields?
We don't apply absolutely different magnetic fields because all samples are paramagnetic in these temperature ranges, and we should apply large enough magnetic field to see high quality signal of the samples. So if we vary magnetic field, the result will be the same. It not depends on magnetic fields.
Thank you.
Okay, are there any other questions? Well, if not, then let's thank all speakers of this session, and we have a break of 25 minutes and we are back soon for the next session. Thank you.
Thank you.